C# and AI Masterclass by Edgar Milvis Volume 4, Chapter 5. Turning our attention to Chapter 5, Converting Legacy Sync Code to Async Patterns. Now, let's talk about theoretical foundations. The transition from synchronous to asynchronous programming in C# is not merely a syntactic change, it is a fundamental architectural shift in how applications manage time and resources. In the context of AI pipelines, where operations are dominated by I/O-bound tasks, network calls to large language models, LLMs, database queries for vector storage, and file system operations for document ingestion, this shift is critical for performance and scalability. Synchronous code, while linear and easier to reason about initially, imposes artificial bottlenecks that prevent an application from fully utilizing the underlying hardware, particularly when handling high-concurrency workloads typical in AI-driven services. Now, let's explore the nature of synchronous versus asynchronous execution. To understand the necessity of the async and await keywords, one must first visualize the execution flow of synchronous code. In a traditional synchronous model, the execution thread is a single, continuous line of instruction. When the program encounters a blocking operation, such as waiting for a database query to return a result or an HTTP request to an LLM API to complete, the thread is forced to sit idle. It cannot process other requests, update the UI, or perform background calculations. It simply waits. Imagine a chef in a kitchen who follows a strict linear recipe. If the chef puts a pot of water on the stove to boil, an I/O-bound operation that takes time, and stands there watching it until it boils, no other dishes can be prepared. The kitchen, the CPU, is occupied, but effectively doing nothing. This is the synchronous model. The resource, the chef/thread, is tied up waiting for an external event. Asynchronous programming, specifically utilizing the task-based asynchronous pattern, TAP, which is the modern standard in C#, decouples the initiation of an operation from its completion. When an asynchronous operation is started, the thread is released back to the thread pool to handle other work. When the external operation completes, e.g., the water boils, or the LLM returns a response, the runtime schedules the continuation of the logic to run on an available thread. The async and await keywords in C# are syntactic sugar that compiles down into a complex state machine. This state machine tracks the execution context, local variables, and the point of suspension. When the await keyword is encountered, the method returns a task or task et object to the caller immediately, representing the ongoing operation. The thread is not blocked, it is free to execute other code. Turning our attention to the critical role in AI pipelines. In AI application development, specifically within the context of building asynchronous pipelines as discussed in Book 4, the shift to async is not optional, it is a requirement for responsive systems. Consider a typical RAG, Retrieval Augmented Generation, pipeline. 1. Input reception, the application receives a user query. 2. Vector search, it queries a vector database, e.g., Pinecone, Milvis, or a local SQLite/face instance, for relevant context. This is a network I/O operation. 3. Context augmentation, the retrieved documents are formatted and sent to an LLM, e.g., GPT-4 or a local model, along with the user's prompt. This is another network I/O operation. 4. Streaming response, the LLM returns a stream of tokens. This requires reading from a network stream in chunks. In a synchronous model, a single request would tie up a thread for the duration of the database query, the network latency to the LLM, and the time required to generate the response. If 100 users make simultaneous requests, you would need 100 threads sitting idle, consuming memory, stack space, while waiting for I/O. This is inefficient and limits scalability. By converting this pipeline to an asynchronous pattern, the application can handle thousands of concurrent requests with a small number of threads. While one request waits for the LLM to generate a token, the thread is free to process another request's database query or handle the response of a different user. Let's discuss the state machine and compiler transformation. The async keyword signals to the C# compiler that the method contains asynchronous operations. The compiler transforms the method into a state machine class. This class captures the method's local variables and the current execution point. When await is called on a task, 1, the method checks if the task is already completed. If so, execution continues synchronously. 2, if the task is not completed, the state machine suspends the method and returns an incomplete task to the caller. 3. The thread is released. 4. When the awaited task completes, either by finishing or throwing an exception, the runtime schedules the continuation of the state machine. This restores the local variables and resumes execution right after the await. This mechanism is distinct from older patterns like task, wait, or .result, which are blocking calls that deadlock the application if used incorrectly in UI or ASP.NET contexts, due to thread starvation. Now, let's explore handling legacy synchronous code and blocking operations. A major challenge in refactoring legacy AI applications is dealing with synchronous libraries. Not all libraries support async natively. For example, older database drivers or CPU-bound libraries, like a legacy image processing library used for pre-processing input data, might only offer synchronous APIs. In these cases, wrapping the blocking call in task, run or using task completion source is necessary. However, one must be careful. Task, run pushes the work to the thread pool. For I/O bound work, this is often redundant if the underlying API supports it, but for CPU-bound work, like calculating embeddings for a large batch of images, it is essential to offload the work to avoid blocking the main thread. Consider a legacy synchronous method that calculates a complex mathematical model. Here, we're looking at a classic example of a synchronous method, calculate complex model. Notice how it's designed to perform a CPU-intensive calculation, simulated by thread, sleep, 5000, at line 5. This thread, sleep call is a placeholder for any operation that ties up the CPU for a significant duration, like complex mathematical computations, data transformations, or AI model inferences that don't involve waiting for external I/O. The critical implication here is that this method will block the calling thread for the entire 5-second duration. In a web application, if this method is called on the main request processing thread, it means that thread cannot handle any other incoming requests until calculate complex model completes. This can severely bottleneck your application's throughput and responsiveness, especially under heavy load. We'll explore how to address this blocking behavior in later examples using asynchronous patterns. To integrate this into an async pipeline without blocking the calling thread, we wrap it. Here, we're defining an asynchronous method named calculateComplexModelAsync. Notice the async keyword, which is crucial. It signals to the C# compiler that this method can contain await expressions, allowing it to pause execution without blocking the calling thread. This is a fundamental pattern for building responsive applications, especially in UI-heavy or server-side scenarios where blocking can lead to a frozen user interface or degraded server performance. The method takes a string data as input and is designed to return a task double, indicating that it will eventually produce a double result asynchronously. This task object is a promise for a future result. This pattern is vital when integrating legacy code into modern AI pipelines, ensuring that heavy computational tasks do not freeze the application while waiting for I/O operations to complete. Let's discuss thread safety and context preservation. When converting synchronous code to async, thread safety becomes a paramount concern. In synchronous code, execution is single-threaded, per request, so shared state is often accessed without locks, though not recommended. In async code, the continuation of a method might execute on a different thread than the one that started it. For example, in a UI application, WPF/WinForms, the UI thread has a synchronization context. When a wait completes, by default, it attempts to resume the method on that same context to update the UI. In server-side applications, ASP.NET Core, there is no synchronization context, so continuations run on arbitrary thread pool threads. If legacy code relies on thread local storage or thread.current principle without capturing the context correctly, data might be lost or corrupted. The await keyword captures the current synchronization context, if present, and restores it upon continuation. However, if you are doing high-performance server-side processing, you might explicitly configure await, false, to avoid the overhead of context switching, but this requires ensuring that no code after the await relies on the original context, e.g., accessing UI elements. Now, let's talk about the event loop and concurrency models. In C#, the event loop is managed by the task scheduler and the thread pool. Unlike languages like JavaScript, which have a single-threaded event loop, C# utilizes a multi-threaded pool. However, the logic of non-blocking I/O is similar. When we await a network request to an LLM, the underlying socket operation registers a callback with the operating system. The OS notifies the .NET runtime when data is available. The runtime then queues the continuation to the thread pool. This allows the application to maintain high throughput with minimal threads. For AI pipelines, this is crucial when implementing streaming LLM responses. Streaming involves reading a continuous flow of data chunks. In a synchronous model, a loop would block waiting for each chunk. Here, we're looking at a classic synchronous streaming pattern. Notice how the while loop continuously calls stream, read, buffer, 0, buffer, length. This method is inherently blocking. It means that the current thread will pause its execution and wait until enough bytes are available to fill the buffer, or the stream ends, before it can proceed to the next line. This can be problematic in high-performance or interactive applications, as it ties up a thread that could otherwise be doing useful work, leading to potential UI freezes or reduced server throughput if many clients are performing similar operations. In an asynchronous model, the loop awaits the read operation, allowing the thread to do other work between chunks. Here, we're diving into the heart of asynchronous streaming, a fundamental pattern for handling I/O bound operations efficiently without blocking the executing thread. Notice how the comment at line 1 explicitly states asynchronous streaming, non-blocking, setting the stage for the code that follows. This approach is absolutely critical in modern applications, especially for servers that need to handle many concurrent requests or for client applications that must remain responsive while performing long-running data transfers. If we were to use a synchronous read operation here, the thread would halt its execution until the entire buffer was filled or the end of the stream was reached, potentially leading to unresponsive user interfaces or bottlenecked server resources. The bytes read variable at line 2 is a crucial sentinel. It will store the number of bytes actually read in each iteration, which might be less than the buffer's capacity, especially at the end of a stream or if data arrives in smaller chunks. This distinction is the difference between a UI freezing while a large file downloads versus remaining responsive. Turning our attention to architectural implications for AI systems. Refactoring legacy sync code to async patterns fundamentally changes the architecture of AI systems. 1. Backpressure and flow control. In async pipelines, if the producer, LLM generation, is faster than the consumer, database write or UI rendering, memory usage can spike. Async streams, async enumerable T, in C#, allow for pull-based consumption, where the consumer requests the next item only when ready, naturally implementing backpressure. 2. Error handling. Async code requires different error handling strategies. Exceptions thrown in asynchronous methods are captured in the task object. They are rethrown when the task is awaited. This requires careful placement of try-catch blocks around await expressions rather than inside the synchronous method body. 3. Cancellation. Long-running AI tasks, e.g., generating a long story, should be cancelable. The cancellation token pattern is integral to async methods. It allows a request to be aborted mid-operation, freeing up resources immediately. Legacy synchronous code rarely handles cancellation gracefully, converting it requires injecting cancellation token checks into long-running loops or blocking calls. Now, let's explore analogy, the restaurant kitchen, revisited. To solidify the concept, let's expand the kitchen analogy. In a synchronous kitchen, legacy code the head chef, main thread, takes an order, user request. They chop vegetables, CPU work. They put a steak on the grill, I/O, waiting for heat. They stand at the grill watching it cook. They cannot chop vegetables or plate other dishes while waiting. If 10 orders come in, you need 10 chefs, or the kitchen becomes overwhelmed and orders take forever. In an asynchronous kitchen, async/await the head chef takes an order. They chop vegetables, CPU work. They put a steak on the grill and set a timer, initiating I/O. They immediately move to the next order to chop vegetables or plate a dish, thread is free. When the timer rings, I/O completion, they flip the steak, resume execution. This single chef can manage 10 orders simultaneously, only spending active effort when something needs to be done. Turning our attention to visualizing the execution flow. The following diagram illustrates the difference in thread utilization between synchronous and asynchronous execution in an AI pipeline scenario. This diagram contrasts synchronous execution, where a single thread is blocked while waiting for an AI model to generate a response, with asynchronous execution, where the thread is freed up to handle multiple other tasks concurrently during the wait. Now, let's explore integration with modern C# features. As we move forward in Book 4, we will leverage modern C# features that build upon this async foundation. For instance, async enumerable T essential for streaming LLM responses. It allows an AI pipeline to yield tokens as they are generated without buffering the entire response in memory. Value task ET used for high-performance scenarios where an operation might often complete synchronously, e.g., reading from a cached memory stream. It reduces heap allocations compared to task ET. Channel ET provides a thread-safe queue for producer/consumer patterns, ideal for decoupling the ingestion of data from the processing in AI pipelines. Now, let's talk about conclusion. The theoretical foundation of converting legacy sync code to async patterns rests on the understanding that I/O operations are orders of magnitude slower than CPU operations. By utilizing async and await, we transform the execution model from a rigid, blocking sequence into a fluid, non-blocking flow. This allows AI applications to handle massive concurrency, remain responsive, and efficiently utilize system resources. The next sections will detail the practical steps of identifying blocking calls and applying these patterns to legacy codebases. Let's discuss basic code example. Here is a practical, hello world level example demonstrating how to convert a legacy synchronous database call into an asynchronous pattern using modern C#. Now, let's talk about the problem context. Imagine you are building a simple AI-powered chatbot that needs to fetch user preferences from a legacy SQL database before generating a response. The original code uses synchronous ADO.NET calls, execute reader, read, which block the entire thread while waiting for the database. In a high-concurrency AI application, this blocking behavior prevents the server from handling other incoming requests, drastically reducing throughput. We will refactor a synchronous getUserPreference method into an asynchronous getUserPreference async method. Let's discuss code example. At the top, we're importing necessary namespaces. Notice system, data and system, data.SQL client. These are fundamental for interacting with SQL Server databases using ADO.NET. System, data.SQL client specifically provides the classes for SQL Server, while system, data offers more general data access functionality. System, threading, tasks is crucial for asynchronous programming, enabling us to work with task objects which represent operations that can complete asynchronously. Here, we define our async conversion example namespace, which logically groups related classes. Inside, the user profile service class is declared. This class encapsulates the logic for retrieving user profiles, making it a good example of the single responsibility principle. The constructor at lines 12 to 15 takes a connection string. This is a best practice. Injecting dependencies like connection strings makes the class more testable and flexible, as it doesn't hard-code environment-specific details. We're now looking at the getUserPreference_sync method, which represents the before state of our asynchronous conversion. Notice the comment at lines 20 to 21, this method blocks the thread while waiting for the database. This is the core problem we're addressing. When this method executes, the thread that called it becomes idle, waiting for the database I/O to complete. In a web server or an AI application handling many requests, this can quickly lead to thread pool exhaustion and poor scalability, as many threads are tied up doing nothing useful. Observe lines 26 to 32. Here, we establish a SQL connection and then immediately call connection open. This open method is a synchronous, blocking call. The calling thread will literally stop execution and wait until the TCP handshake with the database server is complete and the connection is established. In a high-concurrency scenario, if many requests simultaneously try to open connections, they will all block threads, leading to a backlog and degraded performance. The using statement ensures proper disposal of the connection, even if errors occur. Continuing with the synchronous method, lines 33 to 47 show the execution of the SQL command and reading of results. SQL command is created, parameters are added, and then command.executeReader is called. This, too, is a blocking operation. The thread waits for the database to process the query, send the results back over the network, and for the data to be fully buffered. Similarly, reader, read, is synchronous. Each of these blocking I/O operations ties up a thread, preventing it from serving other requests. This is particularly detrimental for AI applications that might need to fetch data for many concurrent inference requests. Now we transition to the after state, the getUserPreference_async method. The most significant change is the async task string signature. The async keyword tells the compiler that this method can use await to pause execution without blocking the calling thread. Task string indicates that the method will eventually return a string, but it does so wrapped in a task, allowing the caller to await its completion. The comment at lines 51 to 52 highlights the key benefit. This method releases the thread while waiting for I/O. This is fundamental for scalable I/O bound operations. Look closely at lines 58 to 62. We're now using await using var connection equals new SQL connection _ connection string. The await using syntax is a C number 8 feature that combines await with using, ensuring that the disposeAsync method, if available, is called asynchronously when the object goes out of scope. More importantly, await connection.openAsync is called. This is the asynchronous counterpart to open. When openAsync is invoked, the underlying network I/O operation begins, but instead of blocking the current thread, control is immediately returned to the caller. The thread is free to do other work, significantly improving throughput for I/O bound operations. Continuing the asynchronous pattern, lines 63 to 79 demonstrate the asynchronous execution of the command and reading of data. We again use await using for the SQL command and then await using var reader equals await command.executeReader async. Both executeReader async and reader.read async are asynchronous. When execute reader async is called, the query is sent to the database, but the thread is released. When await reader.read async is called, the thread is released while waiting for data to arrive from the network. This non-blocking nature is crucial for high-performance applications, especially in environments like web servers or AI services that handle many concurrent requests, as it maximizes the utilization of available threads. Here, we move into our program class, which serves as the entry point and simulation for our demo. The main method is declared as static async task main, string, args. Making main async is a modern C# feature that allows us to use await directly within the application's starting point, simplifying the demonstration of asynchronous operations. At line 90, we print a starting message to the console, indicating the beginning of our asynchronous conversion demo. At lines 92 to 97, we're setting up our user profile service. Notice the mock connection string. This is a placeholder. In a real application, this would be a valid connection string to a SQL Server database. The comment explicitly states that it won't actually connect in this demo, but the architectural pattern of passing the connection string to the service constructor remains important. It promotes loose coupling and makes the service more adaptable to different environments or database configurations without modifying its core logic. The try block at lines 98 to 106 shows the actual invocation of our asynchronous method. At line 102, we call await service.getUserPreference_async, user ID, 42. The await keyword is critical here. It tells the main method to pause its execution until getUserPreference_async completes its work. However, crucially, await does not block the thread. Instead, it allows the current thread to return to the thread pool and handle other tasks while the I/O operation, database query, is in progress. Once the database operation finishes, the remainder of the main method will resume on an available thread. This is the essence of non-blocking asynchronous I/O. Finally, we have the catch block and the concluding message. The catch, exception X, at lines 107 to 112 is a standard error handling mechanism. In a real-world AI application, errors during data retrieval would need robust handling, perhaps involving logging, retries, or even triggering an AI-driven error correction loop. The console.writeLine statements provide feedback on the demo's progress, and the final line at 115 signals the completion of the demonstration. This structure ensures that even if database operations fail, the application can gracefully report the issue. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. This lesson is excerpted from Volume 4, Chapter 5 of the C# and AI Masterclass ebook series and from the volume Asynchronous AI Pipelines. Async/await, parallelism, and streaming LLM responses. You can find all source code here, https://github.com/edgarmilvis/C# programming series. The ebook includes 20 chapters, each one with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. Thank you for your attention. I look forward to seeing you in the next lesson.